Now we consider the work done by the resonating force of the spring. So what is the resonating force of the spring? Let's consider the spring. So assume that the spring is massless, okay, and if you have the original length equal to this value, so let me change here, original length of a massless spring. So now we can say that this position is going to be the equilibrium position of the spring. Let's define equal to be the x equal to the 0. So now if we have some external force on the applied force that try to extend the spring from this position, right, from this equilibrium position to this position, so then we can say that this is going to be the extension of the spring. Okay, let's say the x, which is equal to the x tension of the spring. So if we release the spring, what will happen? The spring try to go back to its original length, right? In this case, it means that it must have another force that try to pull the spring back to its original length. So this is called the restoring force of the spring. We use the symbol as the Fs. Okay, the F. Oops. Okay, we use symbol as the Fs, which is called the restoring force of the spring. But then on the hand, if we have the spring at its original length here, and then if we have some external force or the applied force that try to push the spring to this position, so now you can see that the spring is compressed, right? The spring is compressed from its equilibrium position from the x equal to 0 to this position. So this will be equal to the x. So it's just called the compression of the spring. Okay, so it means that the spring can be extended or can be compressed as well. And if we release the external force, what will happen? The spring try to go back again to its original length, right? Then in this case, it means that the resulting force of the spring will just go into this direction. Okay, so this could be the Fs. So then from an experiment, okay, we can see that the external force on the spring is, okay, so the Fext is going to be equal to the k and then times the x. So the k here just called the spring constant. It's called the spring constant. It will have unit as Newton per meter, okay, because this is Newton and this is meter. So the k is called the spring constant. So if the k is large, so it means that it's going to be quite difficult, okay, to pull or to push or to compress the string. But now if the k constant is small, it means that the spring is easily to be extended or to be compressed. Okay, so that's going to be the physical meaning of the spring constant or the k value here. But then how about if we just want to find the restoring force of the spring? Okay, so now you can see that the Fs is always in the opposite direction to the extension or to the x, right? For example, if the x go to the right, Fs go to the left, and then if the x go to the left, so the Fs go to the right. Then in this case, we can just write our equation as the Fs equal to negative of the kx, right? So you can see that this negative side, right, this negative sign, it just means that the fs and the x, right, we have the opposite direction. Okay, if you have the opposite direction, so this equation is called Hooke's law. Okay, it's called the Hooke's law. Actually, the names of the Hooke's law here is not let's stick only to the spring. Okay, it can be something or some object that can extend as well, but now the extension of that object and the applied force must proportional to each other. Okay, for example, it can be applied to some rubber band or something like that. Okay. So then again, right, we just want to find the work done on the spring by the fs. Let me see first. Okay, so we just want to find the work done on the spring by the fs, by the resulting force of the spring. Actually, you have seen this one already. Okay, you have seen this one already from where, right? So let's go back to the variable force here. Okay, so you can see that we have this one. Okay, so we have the f equal to the minus kx, right? And we can just do the integration, or we can just find the area under the graph, right? And finally we can see that the work done by this force, okay, equal to minus k over 2, and then x2 square minus the x1 square. So here we just do the same thing. Okay, so we just do the same thing, but we're not gonna repeat this one. Okay, we just do the same thing, and then finally we can get that the work done on the spring by the fs, right? Let's use ws here, is gonna be equal to, okay, actually I should make the copy. This is the answers, right? Okay, let me just make the copy here. Okay, so let me just distribute k over 2 into these two terms. So I have the minus of the, okay, the 1/2 k x2 square, and then minus the 1/2 k the x1 square, right? Okay, and then again, right, if we just do the same thing for the work done on the spring by the external force, okay, if we just do the same thing for the work done on the spring by the external force, then the difference must be this negative sign, the same as this gravity here, right? This is the negative sign, and for the external force we don't have the negative sign here. Okay, then again we can get that the work done by this external force is going to be equal to the 1/2 k x2 square, and then minus the 1/2 k and x1 square. Okay, so now let's define. Okay, so let's define the elastic potential energy of a spring. Okay, the elastic potential energy of a spring. So we use the symbol as let's say the US, right? So this S just stands for the spring. What is this? It is the energy which is stored inside the spring when the spring is extended, okay, is extended or compressed, oops, or compressed, wait, is extended no wait from the equilibrium position. Okay, so that's be the definition of the elastic potential energy of the spring. So that's be the energy stored inside the spring where the spring is compressed or extend from its equilibrium position here. Okay. So then don't forget that at the equilibrium position, right, the x equal to the 0. Okay, so then we can define the us equal to the 1/2 the k times the x square. Okay, we just define the us equal to the 1/2 times k times the x square here. So then finally we can get the relations between the work done by the resulting force of the spring, right, and then the change in the elastic potential energy is okay. So now let's look at this equation. We have ws, right, equal to minus, okay, so this is the u2 and the u1, right, then we have delta u here, we have delta us which is equal to minus of the us2 and then minus the us1, okay, which is equal to minus of the 1/2 k x2 square minus the 1/2 k and the x1 square, and that's it. Oops. Okay, so I'm gonna show you how to use this type of the equations later. Okay, so but I mean we can apply this equation to the work energy theorem and then to the kinetic energy as well.